Hello, hi guys, welcome to Chemistry Bite, myself Mubarak. So in this lecture we are going to discuss the Birch reduction. Already I have made one video on the Birch reduction. So in that video I have discussed how an arenes will be converted into an 1,4-cyclohexadienes. Okay, so along with that I also discussed the mechanism of the Birch reduction and as well as the regioselectivity of the Birch reduction. Suppose if you're having any substituent on an aromatic ring, how a Birch reagent will get reduced the aromatic ring into cyclohexadiene. Suppose if you're having an electron releasing group on aromatic ring, you will get a cyclohexadiene in such a manner that the electron releasing group will be attached to an unsaturated carbon atom. Suppose if you're having the electron withdrawing group on an aromatic ring, if you're reacting such type of aromatic compounds with a Birch reagent, so you will get a cyclohexadiene in such a manner that the electron withdrawing group was attached to a saturated carbon atom. So you can see one example here. So when I am reacting the anisole with the Birch reagent, so you can see here this is the Birch reagent, sodium in presence of ammonia and ethyl alcohol will act as a source. You can see here you are getting an 1,4-diene where the methoxy, which is the plus M group, was attached to a sp2 carbon atom, that is an unsaturated carbon atom. If you want a conjugated diene as a product, it is quite simpler matter to isomerize them using an acid catalyst. Suppose if you got an 1,4-diene, if you want to convert into conjugated diene, so if you add a little amount of acid, it will get isomerized. It will get isomerized to conjugated dienes. In fact, a small amount of about 20% of the conjugated product will be produced anyway in the reaction of the anisole. That means you will get an 80% of an unconjugated diene and 20% of the conjugated diene. So if you want a 100% conjugated diene, so after you're getting the 1,4-diene, so to that if you add a small amount of acid, it will get isomerized to the conjugated diene. In case of anilines, it is impossible to stop the isomerization taking place during the reaction and always gives a conjugated enamine. So this aniline, if you are reacting with the Birch reagent, so it will not stop the reaction at 1,4-diene. So this readily isomerizes the 1,4-diene to the conjugated diene. So you can see here, so this is called as an enamine. So reason is due to high activity of anilines. Birch reagent even will reduce the alkynes too, and it's a good way to reduce them to the trans double bond. So you will get a double bond with E geometry, and the best way to reduce them to the cis alkene is via the hydrogen in presence of the Lindlar catalyst. Suppose if you are reacting an alkyne with sodium in presence of ammonia, so here there is no need of any proton source like the ethyl alcohol. So here ammonia will donate the proton. Ammonia is good enough to donate the proton to the alkyne. So we'll see the mechanism now. Whenever an alkyne is reacting with a Birch reagent, so you will get an alkyne with the trans geometry, or we can say it as an E geometry. Suppose if you want to get an cis or an Z isomer, so very simple, you have to react an alkyne with hydrogen in presence of the Lindlar catalyst. So in case of the Birch reagent, you will get an E or a trans product. In case of the hydrogen in presence of the Lindlar catalyst, you will get an cis or Z product. So coming to the mechanism of the reaction, you can see the first step. So this electron was donated by the sodium to the alkyne. So this pi bond in the alkyne will get homolytic fission, and you can see one electrons on the both carbon atoms. So any one of the carbon will accept the one unpaired electron from the sodium and convert into anion. So you can see here the reactive intermediate here is a radical anion. So you can see the stereochemistry of the second alkyl. So this stereochemistry of the second alkyl is not specific. So whether this radical ion is cis or trans. It was not clear in this step. So after this, radical ion will accept the proton from the ammonia. So this ammonia will give the proton to the radical anion. So this NH3 will come out in the form of NH2 minus, and this two part NH2 minus and that sodium ion, so both will come out in form of the sodamide. So now you can see here you got one radical. So this radical will accept the another electron from the sodium atom, and it will convert into a vinyl anion. So you can see here this is converted into vinyl anion. So the negative charge is present in the sp2 carbon atom. The vinyl anions are geometrically unstable and chooses to the E geometry. If the vinyl anion is trying to get the jet geometry, it was highly unstable anion. So what this vinyl radical will do? So vinyl radical will get stabilized by the E geometry. The next step is this ammonia will accept, this ammonia will donate the another H plus ion, that's another proton to the vinyl radical, and will give an E product. So total number of sodium atoms you have used here, you can see here the first electron was donated by the sodium atom here, and the second electron was donated by the sodium atom here. So and how many moles of ammonia you have used here? It is very clear from this. You can see the first you have used here, and the second ammonia molecule. So total number of ammonia molecules used is here is the 2, and total number of sodium atom used here is 2. So total you will get the 2 molecules of sodamide. So how many electrons you have added to the alkynes? You have added the 2 electrons to the alkyne. So both you have added in the trans pattern. Birch reagent will also reduces a conjugated system. So remember one point here. So this Birch reagent cannot reduce an isolated double bond. So what is when isolated double bond? So that double bond so which exists alone, isolate. So it cannot reduce the isolated double bond. So Birch reagent only reduce the conjugated double bond. So isolated double bonds are not reduced by the metal ammonia reagents alone, but the conjugated dienes are readily reduced to the 1,4-dihydroderivatives in the options of the proton donors. So like how we have reduced an alkynes to the E alkenes in the options of the proton donors like the ethyl alcohol, here also when you are reducing the conjugated dienes, no need of using any proton source. Okay, ammonia is good enough to donate its H plus ion. So when I am reducing this conjugated diene, so you can see conjugated dienes of pi, sigma and bi. So both the double bonds are separated by the single sigma bond. So when I am reacting this with sodium in presence of ammonia, so you can see here this pi bond will get homolytic fission. Okay, that sigma bond will convert into a pi bond, so you will get a 2 double bond between I will give the numbering for the carbon atom. Okay, this is the first and second and third and fourth. So between 2 and 3 you got the pi bond. Again on the first carbon atom you have added one hydrogen. Again on the fourth carbon atom you have added one hydrogen. So that is why this will call it as 1,4-dihydroderivatives. Okay, so first as well as the fourth carbon atom you have added the hydrogen, that is why we will call it as 1,4-dihydroderivative. So like how an alkyne followed the radical anion mechanism, so this conjugated double bonds, these conjugated alkenes will also follow the radical anion mechanism. For example, here you can see this is also one conjugated system. So when I am reacting this conjugated system with the Birch reagent, that is sodium in ammonia, so very simple. So I'll give the numbering for the carbon atom. So 1, 2, 3 and 4. So what you have to do is between 2 and 3 we have to write one double bond. So you can see here this double bond you can see between 2 and 3 carbon atom, and on the first carbon atom you have to attach one hydrogen, as well as on the fourth carbon atom you have to attach one hydrogen. So between 1 and 4 you have added the 2 more hydrogen. So this is called as an 1,4-dihydroderivatives. So Birch reagent even will reduce an alpha beta unsaturated ketone. So what is meant by an alpha beta unsaturated ketone? So you can see one example here. So here you can see the functional group is ketone here. What is meant by an alpha carbon? The carbon which is directly attached to the functional group, this is an alpha carbon, and the adjacent carbon to the alpha carbon will call it as a beta carbon. So this is called as an alpha beta unsaturated ketone. So alpha beta unsaturated ketones will react with a Birch reagent. So here when we are using the proton source, so we can see here what we have done. So 2 hydrogen from the proton source was added. Okay, this double bond will convert into single bond like this. C double bond C was reduced and 2 hydrogens you have added. So one hydrogen you have added on the alpha carbon atom and another hydrogen you have added to the beta carbon atom. So alpha beta unsaturated ketones, so when you are reacting with the Birch reagents, it will get converted into the ketones, and how that alpha beta double bond will get reduced to the C single bond C. So coming to the mechanism of the reaction, the first step is electron will get the sodium will donate the one electron to the oxygen. So you can see here between the oxygen and the carbon, that pi bond will get homolytically cleaved, and at the same time the alpha beta double bond will also get participating in the homolysis. This electron which was donated by the sodium will be accepted by the O radical, and the O radical will convert into O minus ion. So now we can see between this 2 carbon atoms, so you will get one new double bond here, and if 1 2 3 the third carbon atom is having the free radical, so you can see here there is the formation of the radical ion. So next step is the proton donor, like the ethyl alcohol will donate its proton to the O minus ions. Okay, this is the first step. So this electron was came from this lithium or the sodium atom, and this hydrogen was donated by the ethyl alcohol. So total this 2 will come out in the form of the sodium ethoxide. Now there is a formation of the free radical. So free radical is highly reactive. This accepts the another mole of electron from the sodium atom and convert into the anion. So this anion, you can see it is negatively charged carbanions will accept the hydrogen from the oxygen, and it will convert this molecule into the enolate ion. So what is meant by enolate ion? So you can see here you're having the double bond and you're having the OH here. Okay, it's a salt of enol, so we are calling it as an enolate ion. So okay, now what about the role of this enolate ion? Suppose if you're reacting the enolate ion with another proton source, so simply that enolate ion will convert into the enol, and it will participate in the keto-enol tautomerism, and you will get the ketone as a final product. Suppose if you are reacting the enolate ion with another nucleophilic donor, suppose if I am reacting this enolate ion with the R minus Ri, that is an alkyl iodide. So this alkyl iodide will generate another electrophile called R plus, the carbocation. So this carbocation, so where it attacks? So it attacks, you can see this pi bond will polarize towards this carbon, and this will get the negative charge, and here this carbon will get the positive charge. This carbanion will accept the carbanion, okay, carbocation. So this alkylation has happened here, and there is no alkylation on the least steric hindered. So remember this point. So after the formation of the enolate ion, this enolate ion, if I am reacting with an alkyl iodide, that alkyl part of the iodide will attack that side of the enolate, so where it is the more steric hinder, so more alkyl group where it present, there it will be attacked. So there is no alkylation on the least steric hindered group, but there is an alkylation on the most steric hindered group. So instead of reacting the enolate ion with an alkyl iodide, so if you are reacting with any other proton source, so you will get a ketone as a product. So you can see one reaction here. So this is a cyclic alpha beta unsaturated ketone. The first step is when I am reacting the cyclic alpha beta unsaturated ketone with the Birch reagent. So you can see the first step, there is a formation of an enolate. So very simple, this pi bond will polarize here, and the same time this will get polarized here, and this will get the negative charge, and we can put lithium on the oxygen. And so here you have tried the new double bond between the carbonyl carbon and the alpha carbon. Now you can see see here the 2 new hydrogens we have added here. Okay, so next step is the reaction of methyl iodide. So this methyl iodide, so where it attacks, so methyl iodide will generate an electrophile called Me+. This Me+ will attack on the carbon of which is the least hindered side, so this will get polarized here, so pi bond will get polarized here, and this will give 60% of 1,1 what is its name, so 1,2,3,2,2-dimethyl cyclohexanone. So this is the major product and this is the minor product. So this is how Birch reagent will get reduce an alpha beta unsaturated ketone to the corresponding ketones and ketones. Okay, so so with this I will stop the lecture. So in the next video still we'll see the applications of the Birch reagent, and we are also going to discuss some questions of Birch reagents, so which are discussed in CSIR net and JEE Advanced or in the JAM exams. Thank you very much guys.